In Lab 2, we will be examining the motion of a falling object. The purpose of this lab is to observe the motion of a falling object as it's dropped from rest. We will then analyze the object's motion and construct models for the motion to see the role of weight force and drag force in the object's motion. To do this, we will first observe the object as it falls. We will then graph the motion of the object, create a model for the motion affected by the weight force, and create a model for the motion of the object affected by the weight and drag force. Finally, we will compare these models to see their effectiveness. Here is the video of the experiment. Here is the tracker program. Using tracker, the length of the flip-flop was determined. The axes were oriented so that it is falling in the negative y direction. As the flip-flop moves, its center of mass is marked and recorded. These data points are then graphed here. Here is the graph of the observed motion shown in higher quality. We will next compare this to a model of the motion of the object when weight force is acting upon it. Here we have two graphs. This first graph is the object's motion. This second graph shows the object's motion and also a computer model for the motion of an object when acted upon by the weight force. The code used to generate this computer model is shown to the right. In this code, the ball's mass was needed to determine the weight force. In this code, the ball's velocity was updated using Newton's second law. Here, Newton's second law is shown as final velocity is equal to initial velocity plus F net divided by mass times the change in time. The net force in this equation is equal to the weight force. The weight force here is the vector of the mass times the gravitational constant. Here, the mass was measured to be 0.22 kilograms, and the gravitational constant was measured to be 9.8. Because the weight force is a vector, it is multiplied by j hat, which gives it a y component. After the object's velocity is determined, it is multiplied by the change in time and then added to the position to update the position. This is done until where the time equals 0.7 seconds, because that is how long the object's motion was observed. Now we will look at the model for an object's motion when it is affected by weight force and drag force. To the left are two graphs. The first graph is the graph from the previous slide, which shows the observed object and the model that is only affected by weight force. The second graph shows the observed object and an object that is affected by weight and drag force. On the right-hand side of the slide is the code for the model, which includes drag force. In this model, weight force is kept the same, however drag force is introduced. Drag force is equal to 1/2 times the air density times the magnitude of velocity squared times some constant multiplied by the surface area. However, this was simplified to a coefficient times the magnitude of velocity squared. The proportionality constant was determined using trial and error as 0.316. In the lower section of the code, most was kept the same. However, the net force was set equal to weight force plus the drag force, where drag force was equal to the proportionality constant times the velocity magnitude squared. In order to get the magnitude of the velocity, the function mag was used in Python. The differences between the two models are reflected in the graphs. In the first graph, which only includes the weight force, the model shows that the position increases constantly at an increasing rate because the acceleration is positive and non-changing. However, in the second model, as velocity increases, the acceleration decreases towards zero. And as the acceleration reaches zero, the velocity stops increasing, reaching some terminal velocity. This term will be explored later. In further analyzing our data, we ask, which model, if any, predicts a terminal velocity, and how so? Shown on the previous slide, the second model predicts a terminal velocity, where the velocity becomes constant over time. In further analyzing our data, we ask, which model, if any, predicts a terminal velocity, and how so? Shown on the previous slide, the second model predicts a terminal velocity, where the velocity becomes constant over time. This is due to the drag force increasing until it is equal to the weight force. The first model, which only includes weight force, does not show a terminal velocity because acceleration is never changed. Therefore, velocity keeps increasing. Another question to examine is whether an initial velocity will affect whether an object reaches terminal velocity, and where this terminal velocity is reached if this occurs. When looking at a model where the same object has an initial velocity of negative 0.5, it is clear that the object still reaches terminal velocity, where the change in position over time becomes relatively constant. However, this velocity is reached at a different displacement than when the object has zero initial velocity. Because the initial velocity is negative and the terminal velocity is negative, giving it initial velocity will cause the object to reach its terminal velocity quicker than when it had zero initial velocity, as shown here. This is only true when the initial velocity does not surpass the terminal velocity. This concludes our analysis. In conclusion, models with weight force and drag force are able to show the terminal velocity because eventually the acceleration will become zero, which will leave the velocity constant. Models with just wave force won't be able to predict the motion of an object falling as the object reaches its terminal velocity, because as it reaches its terminal velocity, the object in reality will cease to increase in velocity. However, the model with just wave force will continue to accelerate. Thank you.